We were discussing the single stage op amp, and the last bit that was left to discuss was the noise and offset. Okay, both analysis are the same. You have incremental currents across each current source, and you find the total output current as a result of all of these. Then you have to substitute either the spectral density or the variance of these currents to find out the variance of the total output current. But of course, commonly you specify the input referred noise or input referred offset. So you divide the output current spectral density or the output current variance by GM1 square to get the corresponding input referred noise spectral density or the input referred mismatch offset variance. Okay. So we saw that in the single stage op amp. Again, I am repeating these things because as we go forward, we will use this differential pair in pretty much every one of our op amp designs. Okay. So if you look at this output current, we see that the tail source M0 doesn't contribute to it because it is injected to the tail node, and that's a general result. Any current injected to the tail node is cancelled to first order. Then all the other incremental currents come out equally. Okay, so if it will turn out that it will be depending on which way you take, some plus and minus could be swapped. So now, because these are from different components, they'll all be uncorrelated. So we saw that the output noise spectral density is 8/3 kT or 16/3 kT times GM1 plus GM3, and the input referred noise voltage spectral density is that thing divided by GM1 squared. Okay, so you will get 16/3 kT by GM1. This you would get if you just have the input pair, you will always get this. Okay, so this is just like if you have some conductance G, you will always have a noise current 4 kT G in parallel or a noise voltage 4 kT divided by G in series. So this will always be there. If you try to realize the transconductance GM1, you will end up getting this with a differential pair, right? And then this second part denotes the overhead because of having the load. Of course, you can't operate without the load, but if you want to reduce this overhead, you have to reduce GM3, which means you have to operate those transistors with a higher VGS minus VT because the currents, everything is the same. So typically, whenever we are discussing trade-offs and changing some parameter, right, it is assumed that you are not changing everything else. Okay, so the op amp has some unity gain frequency. You can't change that because you want to change the noise, right? Because that's a primary specification. The idea is you keep all those things fixed and then you change this. Usually, if you can find a hook like that in any design, that is, your design is working except for one parameter. If you find a hook that influences only that, that will be good. But actually, this is usually not the case. In fact, if you have an optimum design or near optimum, the more difficult it will be to find something like this, because if you change something, everything will change a little bit. Okay, so you may have to do a lot more involved thinking to find out how to change only one without changing others, or you have to change multiple parameters so that you change one while others are constant and so on. Okay, and optimum by definition, if you add the optimum, obviously you cannot do this because by definition optimum means you can't go any further below that. Similarly, this is the absolute variance of the output current. What was it? Sigma Vt1 square times Gm1 square plus sigma beta 1 square times I naught square, that is the nominal current, and times 2 because you have it from two transistors M1 and M2, plus this is the variance in the output current, not the relative output current, the output current. Okay, the nominal output current is 0, so it doesn't make sense to normalize this anyway. Okay, but again, you almost never specify the output referred mismatch. So if you VOS is the standard term used for the offset, you have to divide this by GM1 square. Hopefully this part is clear to everyone. I think this analysis itself you have done in some assignment, right? So now you just have to substitute the values. Okay. So what do you get? 2 times sigma Vt1 square. This is again, this sort of makes sense. 2 times sigma Vt1 square. If M1 and M2, you are applying the inputs to them. If their threshold voltage is an error, that error will add directly to the input. Okay. So you expect that Vt1 and Vt2, their errors will add directly to the input. So where you get a variance of 2 times sigma Vt1 square. Plus, of course, from the first one, you will get that part because of the current mismatch. If you want to reduce the effect of current factor mismatch, which region should you operate? I want to reduce the effect of the beta mismatch. Okay, so which region should you operate in? Weak inversion, strong inversion, moderate inversion? Weak inversion. Why? Okay, right, for the input referred mismatch. Weak inversion, yeah. So anyway, this is dimensionless and this has dimensions of voltage. So that will be in weak inversion. Okay, and then you have this, just like the noise case, will get multiplied by GM3 by GM1 square. Okay, and okay, so this is from the input pair and this is from the load. Okay, and of course, if you reduce GM3 by GM1, you will end up reducing the influence of M3, but then of course, you will move it further into strong inversion, it will change the other factor and so on. Okay. But at least if you are not given any other specification, you should at least aim for, let's say, equal contributions from all of them. Now, I have not shown flicker noise. Flicker noise is not fundamental, but it will be there. So it is important in low frequency cases. But the procedure for calculation is the same. Okay. Any questions? So you will have mismatch. And finally, like if you have to reduce mismatch, you have to increase the size of the devices, all devices, because Noise, of course, noise is related only to GM, whereas mismatch is also related to the size, right? There are some process constants ABT and A beta, but it's also related to the size. So all these factors you can see, this, that, and that, all are inversely proportional to the area of the devices, right? So if you increase the area of the device, you will basically have lower mismatch. Is this okay? So with this, basically the op-amp's data sheet is complete, and we can go on to design other things, right? So if you have a spec, now you know how to go about designing the op-amp, okay? Now, of course, you cannot go below a certain offset level simply by increasing the size, because if you had an offset of, let's say, 10 millivolts or 10 millivolts, and then you want to go down to 1 millivolt, how much do you need to increase the area by? The input referred offset sigma was 10 millivolts and you want to go to 1 millivolt. What should you do to? Of course, sizing is an option without changing anything else. How much should you increase the area? 100 times. Okay, this seems like a little too much, right? So we won't discuss that in detail, but yeah, there are sometimes where if this offset is crucial, you have to reduce it, but you can't reduce it by large factors by just sizing. I mean, it becomes too expensive. Okay, or at least this will tell you that if you really want very low offset, you have to use larger sizes, but at the same time, you will end up with larger parasitics. So if you had a high speed circuit, that also has to be accurate. That becomes the most difficult case. Okay. So I won't discuss this part in detail, but I think I had one of the assignment problems also. So let's say, I mean, this 100 times increase in size is infeasible. Okay. So is there some way of reducing the offset without it? I mean, think back to some assignment problem. So basically what in general offset means that let's say you have an amplifier A, okay, so you add offset here. Now if you do this, if you multiply this with a plus minus 1 sequence, and also multiply this again with a plus minus 1 sequence, and these two are aligned, that is the two waveforms are in time alignment. Okay. If you have a memory-less system, that is there is no filtering or anything going on here. So very clearly, any input applied here will go through two multiplications, either by plus 1 or by minus 1 in both cases. So it will just come through as it is. Okay. So from here to there, you just multiply by 1. Whereas the offset is multiplied only by this alternating sequence. Okay. So if you multiply a constant by that alternating sequence, what happens? You will get a square wave which is now modulated by that, you will get a square wave of amplitude VOS, right? So now that is not a DC anymore, okay? So that is at a frequency equal to this chopping frequency and its harmonics. So now if you use a low pass filter, okay, so that will filter out the square wave and you will have no offset, okay. So this is one of the dynamic techniques that is used to reduce offset. Now there are of course many details here. I have assumed that this block itself is memoryless, okay. That is, if there is some filtering and something going on, then this will behave differently, okay. It's not that exactly if you put in a sine wave here, if that sine wave gets phase shifted, what you get out will be something different, okay. So that is one thing. Now one way to think about it roughly in the frequency domain is, Let's call this frequency f chop. So let's say the input signal is at a very low frequency. Okay. What will be the spectrum of the signals over there? This is the input, and let's say this frequency is FCH. So what will be the frequency? What will be the spectrum of the signals over there? What happens when you multiply a signal by a periodic signal? The signal spectrum will get translated to the harmonics of the periodic signal, right? And the conversion gain will be related to the harmonic magnitudes. Okay. So here what happens is you will get FCH minus F in, FCH plus F in, and also you get I'm showing them as just equal amplitudes, but the amplitudes will be different. 2FCH plus minus F in and so on. So it will get translated everywhere. Okay. So now you can clearly see if this block is a filter, right? This block is a filter. What happens is earlier when the input was applied without any of this chopping, the input signal was getting multiplied by the low frequency gain or the DC gain of the filter. Now it will get multiplied by the high frequency gain, okay, which can attenuate. So it's not exactly the same as this chopping is not exactly the same for every circuit as without chopping, right? This plus minus 1 that works only assuming this A does not introduce any significant filtering over that band of frequencies, including the chopping frequency. Okay. So essentially, you will see that whatever low frequency signal is here, it will get translated up to the chopping frequency and then get translated back. So if this block has a lower gain at the chopping frequency compared to DC, then overall effectively the gain has reduced. The analysis is a little more involved. You can do it in detail, but basically that's what happens. Okay. Is that fine? So, but this can be used if your signal band is small, the signal frequencies are small. You also choose a chopping frequency that is relatively small, so that it's not affected by this. And then you can do this chopping to get rid of the offset. Okay. Now it will introduce its own problems because whenever you have switches like this, the switches themselves will have some transients and so on, because you will implement switches with MOS transistors. MOS transistors, when you turn them on and off, they will take in charge, they will put out charge and so on. So those things will come into picture, but this can be used. And also importantly, this can be used for 1 over F noise, flicker noise, because it is just like offset. 1 over F noise and offset behave more or less similarly, because if this VOS for DC, this is a constant. Flicker noise, you can think of it as a low frequency source that will be multiplied once and be translated to higher frequencies, and that will be removed by the filter. Okay. So this technique is called chopping, that is multiplying twice by this 1 minus 1 signal. There are many engineering details to make sure that, because what was earlier a DC picture has now become a transient picture, right? So there are many engineering details to make sure that this works correctly. But with this, you can get very low offsets. Without this, you cannot get offsets in the, let's say, tens of microvolts and so on. Okay. So to have that, you will need some dynamic technique like this. In fact, as the digital switching has improved, you can use dynamic techniques for many things. Okay. So I will just give an example since we came to the topic, but this technique is called chopping. The basic principle is that any signal added between the choppers is moved to high frequencies. Okay. So this is most frequently used for offset and 1 by f noise. Okay. And the input signal is multiplied twice and is not affected. Okay. And this whole thing assumes that whatever block we have in the middle, this A doesn't have substantial filtering over this range of frequencies, including the chopping frequency. Okay. So these dynamic techniques are interesting. That is, I mean, by nature they can be used at low frequencies. But of course, what is low frequencies has been going up as a result of technology advancements as well. Because what is high frequency in for a 180 nanometer circuit can be a medium or low frequency for a 18 nanometer, 16 nanometer circuit. Okay. So you can use these things at higher and higher frequencies, right? So just quickly, another example of dynamic techniques is memoryless. Yeah, memoryless means no filtering, right? Inverted signal meaning? No, the transfer function, there is no implication here that A must be positive. It can be positive, negative. It works in the same way, right? Doesn't really do anything. No, that's what. Then you have memory. If you have memory, then I mean, there can be an issue, right? So you have to make sure that that is small enough. I mean, that's the, huh? What's that? No, no, no. I mean, there's no such thing. It's basically whatever is small enough for that context, right? 5 degrees could be very large in some case and very small in the other case. So let's say you make this inverting amplifier and you want to have a gain of -1. Okay. But what is the problem? These two are different in general, right? There'll be mismatch between them. And again, you can try to make it make the gain closer to 1, closer to -1 by making the resistors larger and larger. But clearly, if the variance in the gain was, let's say, 2% and you want to make it 0.2%, you have to increase the area of the resistors by 100 times. Okay. So in this spirit, what dynamic technique can you think of? Dynamic technique basically means that you may have some time varying circuit which on average behaves the way you want. Okay. So in this case, can you think of something? What could you do? You understand the problem, right? R1 and R2 are slightly different from each other simply because of random mismatch. They have nominally the same value. Okay. Now, we want to make the gain exactly 1 and we are willing to use dynamic techniques. And dynamic techniques by implication means that the signal is at low frequency. This dynamic variation will happen at some higher frequency, which will be averaged out by later filtering, whether inserted deliberately or what is already present in the system or whatever. Of what? But that doesn't do anything, right? Because this, so you're saying, I mean, basically you are saying this, but if this A is different from 1 or -1, then how will that change? The gain from here to there is still A, right? What can you do? The mismatch where? So that is changing the added offset, right? See, the chopping is moving this added signal to a different frequency. It's not changing anything to the multiplication factor, right? If this is A, it will remain A. So here this is 1 point, let's say 0.2 or something. Okay. What can you do? Huh? Yes. The gain magnitude, I want it to be exactly 1. Well, let's say this is the op amp we have. This is the circuit we have. But how will that help differential op amp? But that still doesn't help, right? Let's say the op amp is ideal. Okay, let's not like fool around with the op amp now. The op amp is ideal. What can you do to? No, it is mismatch. I'm saying because of mismatch, the gain is different from 1. I want it to be exactly 1. Okay. Yeah, or how will you produce that? You will have to, if you use 2 different resistors, then you're finished because those 2 will be even 2 more different values. Okay. Yes, Gunasekar, I saw you waving something. I mean, huh? Yeah. So if the gain is like this, if the configuration is like this, the gain would be, let's say, okay. So now, if I put R2 here and R1 there, what will be the gain? 1 minus epsilon. Okay. So I can switch between these 2 configurations. That is, I have 2 resistors, I interchange their roles. Okay. For some time, whatever I identify as R1 is the input resistor, R2 is the feedback resistor. For another slice of time, R2 is the input resistor, R1 is the feedback resistor. Okay. So now, basically, actually, the input signal is getting multiplied by some time varying multiplying factor, 1 plus epsilon, 1 minus epsilon, 1 plus epsilon, and so on. Okay. So again, if the frequency at which you have this alternation is higher, much higher than the signal frequency, on average, it looks like it's getting multiplied by 1. Okay. So these are dynamic techniques that are used. Again, there are lots of details, but at least it's possible. Okay. With this, essentially, the mismatch more or less goes away, right? Of course, this is applicable in a restricted context. Again, you are now dealing with time varying signals, etc., etc. Okay. What is that? Huh. So you're saying that basically here this has noise, right? Right. So basically you have frequency translation by FCH. Any signals you have at the input around FCH will come back to DC. So those things will happen. Okay. So this is not some unless this is perfectly memoryless, this is not some sort of universal solution. If it is memoryless, then this +1 multiplying either +1 twice or -1 twice will cancel. But otherwise, yeah, you will have, you can't have signals around the chopping frequency because that will fall back and it can cause other problems. Okay. So just a minor extension of this. So let's say, again, I won't discuss the implementation, but at least you know that you should know that these things exist, and then you can implement them with some switching network, alternating this and that and so on. Okay. So now, what is it supposed to do? What is it? What is this block? So it should be 5 times this. But of course, again, we have the problem that this is R2, which is nominally 4R, and this is R1, which is nominally R. Okay, but there will be errors. So in this case, can I use some dynamic techniques to make the gain exactly 5? What could I do? Hmm? Yeah. No. Mismatch in the op amp is the input referred offset of the op amp. Mismatch in the resistors is not related to that. Okay. The resistor is not part of the op amp. Mismatch in the op amp's transistors will be input referred offset. Okay. No, this won't cause an offset. No, you can analyze it and see. This will only cause a gain error, right? This is not causing an offset. Okay. So in the op amp, any mismatch in the transistors will give you a non-zero output current, even if there is zero input voltage. That is an offset. But the error in the value of resistors will not do that. It will not give you non-zero output if you have zero input. It will give you zero output. That's all. Only if you have non-zero input, it will multiply it by some incorrect factor. So what can I do here dynamically? Could I do something? First of all, how would we implement this? I think we discussed some details, right? Some practical details. If I want a gain of 5, I have a resistor 4R and resistor R. How would I implement these in the first place? Yeah. So maybe I would have done 4R would be 4 of them, and then R would be 1. Okay. These are identical resistors, right? So now can you think of some dynamic technique for this? What can you do? Yeah. So you can basically again swap between them. One possibility is you just rotate between them. That is, you have 5 resistors. Okay. So in the first cycle, R5 is R and R1, 2, 3, 4 make 4R. Okay. In the next cycle, maybe you make this R4 and 1, 2, 3, 5. There are many ways in which you can choose. You can just choose randomly, I mean, in a pseudo random way, or you can just rotate through the elements and so on. So, but again, you can, I mean, you will need a massive switching network here. Every resistor must be connected to some switching network. So that, and obviously, when you do that, those switches should not be offering significant resistance, because then that will come into picture. So those are all the practical details, but at least there is some technique that can potentially get rid of the mismatch. Okay. So now you can see the periodicity. If you have many elements like this, the periodicity is 5 times each duration. So either you have to make each duration short, or you have to accept that this cycling happens at a lower frequency, right? So again, we said that this the periodic variation, there should be a difference between the signal frequency that you want to process and the variation of this periodic signal. Okay. So the more elements you have, the more difficult it becomes to keep this at a high frequency. Okay. But anyway, the important thing is to note that dynamic techniques exist, and they can help you sometimes. Okay. And in fact, for offset and gains, right, by brute force increasing the area, there is only limited stuff that you can do. Okay. You may have to do things like this, or you may have to do corrections in some other ways. Okay. Because by increasing the area, getting factors of orders of magnitude improvement is not feasible usually. And in any case, there is always this ultimate limit that I showed, right? As the element becomes bigger and bigger, parts of the element are farther from each other. So it's not as though it will monotonically go as inverse proportional to the area. It will, even the matching will flatten out at some value. Even if you go on increasing the area, there will be some mismatch anyway. Okay. No, I mean, it makes sense to do it through the minimum number that is possible, right? Yeah. I mean, how you, R1 itself could be have 10 strips, or who cares, right? Basically, each unit element you cycle. That's all. Yeah. And of course, I mean, it goes without saying that this need not be series and series combination. It could be parallel also. Okay. So R1 could be 4 of something in parallel, and 4R is just a single element and things like that. And it's the same, no? I mean, you'll have 4 total elements, that's all. However, number of, see, if you do unit element based, you anyway do unit element based layout for accurate matching. Then you cycle through all the unit elements, that's all. So since I brought up the topic, let me just show how to implement the chopping with the op amp. This kind of switching network you see many times, and I label these two switches as phi and these two as phi bar, and schematically this is phi, right? Okay. Maybe I should, yeah, let me not do phi and phi bar, although it is denoted like that. So you have phi 1 and phi 2 will be on in the opposite phase. Okay. This goes to the differential pair. Okay. So now the other thing is that because all transistors contribute to the offset, okay. So by doing this, what happens is in phi 1, M1 is connected to the plus input, and in phi 2, M1 is connected to the minus input. The role of M1 and M2 are interchanged, right? By these control signals phi 1 and phi 2. Similarly, these, they also have to be interchanged. Okay. So that is in one of the phases, M3 must be the diode connected transistor, and you take the output from M4. And in the other phase, the opposite, M4 must be diode connected, and you take output from M3. So you need a switching network here as well. Okay. So it is a little bit messy to draw all the details here, but for the first time around, I'll do that. Okay. Okay. So if you just look at it, what happens is when phi 1 is on, M3 is diode connected and output is taken from there. And when phi 2 is on, M4 is diode connected and the output is taken from there. Okay. And typically, because this thing is so messy, once you understand the structure, this is, you have some sort of symbol for it. You just show some crossover switch like this, which is either direct connection or flip connection. And okay, once you understand the principles, I mean, you will be able to understand this. You have to get used to it though. Okay. And usually a control is shown like this, some phi, but you have to also be careful while operating the switches. This phi 1 and phi 2 cannot be simultaneously on. If they are simultaneously off for a short while, it may be okay. But if they are on, what happens is these two inputs get shorted to each other. Okay. So that should not happen. Right. Same for the output side. Typically, there will be constraints like that also. Those are all details we won't get into now, but this chopping is widely used to reduce the offset and 1 over f noise. Now, because this is a dynamic technique, typically dynamic techniques are confined to low frequency signals. So, you use them for low frequency circuits. But of course, as you go to finer and finer technology nodes, what is low frequency can be many megahertz or even higher. Okay. Any questions? Okay, so now we are done with the single stage op amp. Okay, and we understand all the specifications. So now we move on to higher number of stages. Okay, and then to fully differential op amps. Or maybe, oh, I forgot the cascode op amps. So one of the first way that we thought of improving the gain of the op amp was to use common gate buffers, current buffers for both the differential pair as well as the current mirror load. Okay. So how does this work? You can use a cascode stage on top of this. Okay. And right. So here I am using NMOS cascode for NMOS common gate amplifier. So this is fixed at some voltage VG56. Okay. So that you have to generate and so on. So the circuits quickly will become more complicated, but of course you have to based on your background knowledge, you have to design all these biasing circuits. Okay. And the PMOS current mirror will use a PMOS common gate amplifier. Okay. Okay. Now you connect the current mirror in exactly the same way. That is based on this drain voltage, you vary the gate so that it gets biased correctly. Okay. And this is the output node. I won't go through the analysis of this in detail because you already know how this common source, common gate combination works. Okay. So we'll assume that the tail current is 2 I naught, which will split into I naught and I naught in the operating point. The input is biased at VICM, and on top of that, you can have a differential signal. Okay. Now, what are all the things that will be different between this and the conventional single stage op amp? That is without the common gate buffers or without the cascodes. Gain, clearly, that's the main purpose for using this, and the output resistance is higher in this case, right? So earlier, this if you try to put all the RDSs, all the GMs and analyze it, it becomes extremely messy. You just have to understand that the common source, common gate combination has an output resistance which is approximately GM times RDS of the cascode times RDS of the amplifier device. Okay. So in this case, okay, this is what we had as the gain. So which parts change in this? In the cascode op amp, what happens to GM1? GM1 remains as GM1. Okay. And what happens to RDS1? Approximately it is its cascode device, GM5, right? GM5 RDS5 times RDS1. Of course, there will be plus RDS5 plus RDS1 and so on, which I'll ignore for now. And what happens to RDS3? GM7, RDS7, RDS3. Okay. So while this is of the order of GM-RDS, this is of the order of GM-RDS square. Okay. So that's the advantage we get from the cascode op amp. Other things remain the same. So the DC gain is what is mainly different, right? If you load this with a capacitor CL, what is the unity gain frequency of the op amp by itself, ignoring all the other parasitics and so on? It will stay GM1 by CL, because the current through the cascode doesn't change. Okay. So you have GM1 VD by 2 from this side, which gets mirrored, GM1 VD by 2 from the other side, the two add up and it will give you GM1 by GM1 times VD as the output current, and GM1 by CL will be the unity gain frequency. Is this okay? Okay. So what else will change then? Swing limits you expect to change because there are just so many more transistors stacked. You expect that to happen. We'll write down the expressions for that. What about what else will change? Huh? Poles. Again, there are many more nodes in the circuit. The more nodes you have, the more parasitics you have, and the more poles you have. Roughly speaking, every node will be associated with the parasitic pole, and the number of nodes you have will be the order of the circuit. So there will be many more nodes, many more parasitic poles. Only thing is, if you have a common gate amplifier, this is the common source, common gate, and you have a parasitic capacitance here. What is the pole frequency because of this parasitic capacitance? What will it be? Again, now as of now it is a first order system. So what is the resistance that appears across that capacitor? Yeah, primarily it is the GM of the cascode device. So GM of cascode device divided by CP is the additional pole. So all these additional poles will be of that order. Okay. So we can consider them to be non-dominant poles, or of course you will design them to be non-dominant poles. They will be at high frequencies. Okay, but nonetheless they will be there. So there will be some effect on the phase margin. Other things we'll discuss. What will happen to noise and offset? Noise and offset, what happens? Noise gets no change. Why? The cascode devices don't contribute to that, and the same happens for mismatch. We'll see those things. Okay. Any questions?